In this video, I will give you a very clear description of what recursion is, and more importantly, I will give you a systematic approach that you can apply to every recursive problem. We will start by covering the fundamentals of recursion, and next I will show you how to visualize the solution using the recursion tree. I will show you how to identify if a problem has a recursive solution, and also I will briefly talk about the runtime complexity of recursive functions. By the end of this video, you won't just understand recursion, you will master it. I will give you a new perspective by showing you the one important pattern that solves every recursive function. So let's get started. First thing first, what is recursion? We call a function recursive if it calls itself. For example, this is the very famous Fibonacci function that calls itself twice. F of n is equal to f of n minus 1 plus f of n minus 2. For every recursive function, you can draw a diagram like this that indicates how this function calls itself. Note that recursion can be indirect. For example, function f can call function g, and then function g can call function f. What is practical recursion? In practice, a recursive function should eventually stop the recursion. For example, for Fibonacci function, once n becomes 0 or 1, we don't have recursion anymore. As soon as the function's input becomes 1, we return 1, or if the function input is 0, we return 0. This is called the base case. So every practical recursion should have a recursive step which tells you how the function calls itself, and it has a base case where it says under what condition the function is not recursive anymore, and it just returns a value. And this base case essentially ensures that the recursion ends. This tree shows how the Fibonacci function calls itself as we go from f of 5 down to other values for f. Oftentimes, as the function calls itself, the parameters become simpler and simpler. So presumably, for example, calculating Fibonacci function on the number 4 or 3 is simpler than the number 5. So there are two pillars to recursion. One is the recursive step, and one is the base case. One more thing about the recursive step, it not only tells you how the function calls itself, which you can see in this diagram, but it also tells you how to combine the result of these two function calls to get the overall solution. So for example, in this case, we have to get the solution of this one, the solution of this one, add them together to get the solution of the overall function. It's a great practice to explicitly specify what this combinator function is for every recursion that you're solving. As you will see, we will get back to this over and over again in this presentation. Note that you can implement loops with recursion. Consider these two loops in which we print the values from 0 to n minus 1. Once I gets to the value of n, we exit these two loops. A loop like this can be implemented using recursion. We basically start from 0 and stop at n. So n can be considered a base case for our recursion. So this is like calling a function for value of 0, then value of 1, then value of 2, all the way to value of n, where we stop and return. So we can write a function like this. It takes two parameters, I and n. If I is equal to n, which is our base case, we simply return and don't do anything. This is exactly what happens in these loops. Once i's value is n, we exit the loop. However, if that's not the case, we simply print I and we call the function for I plus 1. So assuming we call this function from I is equal to 0, this function will be called for I is equal to 0, 1, 2, and all the way to n. The end result would be the same thing that this loop would do, printing the values from 0 to n minus 1. This sort of function is sometimes called tail recursion, which means the last thing that we do in the function is returning a value from the recursive call. So in this case, the value that I return is exactly the value that I get from my recursive call. This is called tail recursion. And in general, if the diagram of your recursion call looks like a linked list, looks like a chain of functions rather than a tree, that's a very good indicator that your recursion is actually implementing a simple loop. It is very important to understand other problem-solving concepts that lead to recursion. There are other terms and techniques in computer science which are really recursion, but they have other names. So let's look at some of them. The first one is breaking a problem into subproblems. This is actually not specific to computer science. It's a technique that is used in all fields of engineering. You have a big problem that is hard to solve. In order to solve it, you break it into multiple subproblems. You solve each subproblem and have a solution for each subproblem. Then you combine them and you will get the final solution for your big subproblem. So this is a general technique and it works just fine, but oftentimes in computer science, the subproblems of the problem that you're breaking or decomposing are actually the same problem with a different parameter. So what I'm saying is that if this problem is represented by a function f, these subproblems are also the same function but different parameters. And you guessed it right, this is exactly what recursion is. So in practice, in computer science, oftentimes when people talk about breaking a problem into subproblems, it is very likely that you're actually using recursion. And that involves calling the same function multiple times with different parameters, and then combine the solutions of each of these subproblems to get to the solution of this problem. Another technique is called divide and conquer. This was borrowed from politics, where if you want to conquer a country or a group of people, you first divide them, and then now it's easier to conquer that group or that country. In computer science, however, this is very similar to what we do in breaking the problem into subproblems. But what happens is that we do that breaking part using the division operator. So usually the size of the problem is divided by a constant. For example, here, your original problem is of size n. You break it into two problems where each of these problems is of size n over 2. You could do this in 3 ways or 4 ways or in general in k ways. The key is that you're doing this using division. After this, it's just like before, you solve each subproblem recursively, and maybe you break this into 2 subproblems, you break this into 2 subproblems. Each subproblem, again, has half of the size of this one, and you keep doing this until you get to your base case. Once you have the solution for each subproblem, you combine them, and you get the solution to the overall problem. So divide and conquer is just a special case of breaking the problem into subproblems where you're using division by a constant. There are various examples of this technique. Quicksort, merge sort, and Strassen matrix multiplication are some famous algorithms in computer science that use this technique. Another term that you might hear is called optimal substructure, which is usually discussed in the context of dynamic programming. In dynamic programming, we say, in order to be able to use the dynamic programming optimization, the problem needs to have optimal substructure, which means in order to find the optimal solution, you need to find the optimal solution of the subproblems and then combine them to get the optimal solution to the overall problem. Again, notice that what I said is exactly what we do in breaking the problem into subproblems. And because this optimal function that you have for your subproblems is just the same function here with different parameter, you have recursion. So optimal substructure in practice is nothing but recursion. In order to be able to apply dynamic programming to a problem, you first need to have recursion. There are various examples of dynamic programming and this optimal substructure property in computer science. For example, Bellman-Ford algorithm is one of the most famous ones. There's the knapsack problem, the word distance problem, and other ones. So in summary, when you hear any of these terms, optimal substructure or optimal substructure, divide and conquer, or breaking the problem into subproblems, they all mean one thing, and that is recursion. These are not really completely different techniques. They are very related. All right, so now let's talk about some famous recursive functions. The very first one, probably the most famous recursive function, as we saw, is the Fibonacci function. F of n is equal to f of n minus 1 plus f of n minus 2. As I mentioned before, the combining function between the two subproblems is the add function. Now let's see another one. Factorial is another famous recursive function. N factorial is equal to n by n minus 1 factorial. So if factorial is a function and you call it with the parameter n, in order to solve this, your subproblem would be n minus 1 factorial. So notice the recursion here. And again, notice that our recursion is really a chain or a linked list and not a tree. What is the combining function here? Once I get the solution of n minus 1 factorial, I have to multiply it by n. So I just write multiplied by n is basically the combining function for factorial. Moving on, let's talk about greatest common divisor or GCD function. GCD of a and b, two numbers, two integers, is equal to GCD of b and a mod b. And the base case is that GCD of a and 0 is equal to a. Again, notice that from GCD of a and b, I go to GCD of b and a mod b. This again indicates that we are really implementing a simple loop. Now, you tell me, what is the combining function? Assuming that I break my problem into a single subproblem, what should I do on this to get the solution to the overall function. And hopefully you get it right. In this particular case, the combining function is just replacement. All you need to do is replacing this function by this function. You basically don't need to do anything on this. Up next, merge sort. Merge sort is a very famous recursive function for sorting an array. If you have an array of size n with left index on the left side and right index on the right side, you can break this into two subarrays from left to the middle point and from middle plus 1 to the right point. Merge this one and merge this one. And then you have to combine these two merge sort arrays. So what is the combining function? In this case, there's a very famous algorithm called merge, which takes two sorted arrays and merges them into a single sorted array. Merge sort is kind of special because this merge or this combining operation is not O of 1 like the previous functions that we saw. It is actually O of n. So it takes O of n operations to merge two sorted arrays and get to an array of size n that is sorted. Up next, quicksort. Similar to merge sort, quicksort tries to divide the array into two subarrays, and it works in the following way. It uses one of the elements of the array as the pivot element, and then it puts all the values in the array that are less than the pivot on the left side, and all the values that are greater than pivot on the right side. Notice that the elements here are equal size. Sometimes this happens and sometimes this doesn't happen. Now the pivot element is at its right place because everything on the left side is less than the pivot. Everything on the right side is greater than the pivot. And all we need to do is to recursively sort the left side and recursively sort the right side. Now, what is the combining function here? Notice that because this is already sorted and this is already sorted and everything here is greater than everything on the left, all we need to do is just concatenating them. So you concatenate this subarray on the left with the pivot and then the subarray on the right. The interesting point about the quicksort is that breaking the problem into subproblem, basically finding the left subarray and the right subarray is not O of 1, unlike other functions that we saw in the past, but it is O of n. It takes O of n operations to find the right index of the pivot and put all the values that are smaller on the left and all the values that are greater on the right. Up next is binary search, in which you want to find a value in a sorted array that has index left and index right. In order to do this, you first compare to the middle point. So I have to compare to the middle point. If the value is equal to the middle point, I just return this index. If it's smaller, I binary search to the left side. And if it's larger, I binary search to the right side. So when I break the problem into subproblems, I will have three subproblems. Two of them are recursive. One of them is not recursive. What is the combining function? How do I combine the solutions of these three to get to the solution of this? And in this case, I hope you guessed it right. The combining function can be just the simple OR operation because the index that you're looking for is either this one or this one or this one. And exactly because this is an OR operation, if you see that you have to do binary search on the left side, you can throw out the right side and vice versa. And this is exactly why binary search has a very fast runtime. Moving on, what is the recursion tree and why is it so important? The recursion tree is the visual representation of how f, or your recursive function, keeps calling itself until it gets to the base case. For example, for Fibonacci, if you're calculating f of 5, you have to calculate f of 4 and 3. In order to calculate f of 4, you have to calculate 3 and 2. From 3, you go to 2 and 1, and from 2, you go to 1 and 0. 1 and 0 are your base cases. So all of the leaves are your base cases. You can draw a tree like this for every recursive function, or I should say for every practical recursive function. And it is important because it gives you a lot of insight into how the recursive function is solved. And not only that, it also gives you a lot of insight in how to calculate the runtime and memory complexity. So let's see how that works. Before doing that, let me ask you a question. What is the most important algorithm in computer science? Think about all algorithms that you know in computer science. Find your most favorite one that you think is the most important one. I think everyone can come up with a list or with their top 5 most important algorithms. For me, that algorithm is DFS, depth first search. I picked DFS at the top of my list because it shows itself over and over again in multiple places and a lot of techniques in computer science are based on this important algorithm. So up next, I want to show you how recursion is related to DFS. First, let's remember how DFS works in trees. What is the DFS algorithm in trees? If you have a tree and the root of this tree is given to you, in DFS, you first check to see if the root is empty. In that case, you return. This is your base case. Otherwise, you call DFS on each child node. In this case, I'm showing a binary tree, so I will only have 2 DFS calls. If you have a non-binary tree, you would have a for loop here, and you would just call DFS on each child separately. You probably have seen different flavors of DFS on binary trees in the past. There is pre-order, in which you use or print the node's value before your recursion calls, or there is in order, where you do your print after the first recursion call, or there's post order where you print at the end of both recursion calls. All of these 3 algorithms are nothing but DFS. So what is important to remember is understand how DFS works, and also understand that DFS is inherently recursive. Now that we got a refresher on DFS, let's also look at a recursive function like Fibonacci and compare them side by side. So in Fibonacci function, the first thing that we check is our base case. If n is equal to 0 or n equal to 1, we return n. Otherwise, we will have 2 recursion calls. I call the first one left and the second one right, and then we return the result of left plus right. Look at this Fibonacci function and this DFS and tell me if you see any similarities. In both of them, we have recursion calls, and in both of them, we have check for the base case. The Fibonacci function happens to have one extra step, which is really nothing but the combining of the solutions. So what I'm saying here is that it looks like the recursive Fibonacci function is really the same algorithm as DFS. What we are doing here is nothing but calling DFS. Now, you tell me, here's a question for you. If I am calling DFS, what is the tree that I'm calling this DFS on? Where is that tree? And the answer to that question is that this DFS is called on the recursion tree. So what I'm saying is that it looks like every recursion corresponds to running DFS on its recursion tree. If this is the recursion tree of the Fibonacci function, the DFS that corresponds to it is nothing but running DFS on this tree. So that means running DFS on the left subtree, running DFS on the right subtree. So this means there's this close relationship between recursion and DFS. For every recursive function, you can find a corresponding DFS on its recursive tree. And the DFS function is recursive itself. I know you might feel dizzy, but that is a very interesting relationship between these two, which gives you a lot of insight. So if you look at this diagram one more time, you will see that the root is the problem that we want to solve. The subtrees, this one and this one, are your subproblems, which correspond to your recursive calls. And the leaves are really the base cases. So once you imagine or visualize this tree, in order to solve this recursion, all you need to do is to run DFS on this tree. Why is this useful? One reason is that, first of all, it helps you imagine and visualize how a recursion is solved. Take any recursion of your choice, draw its diagram, and you would see that that recursion is really running DFS on that diagram or that tree. And not only that, this will also give you some insight on the runtime complexity of your recursion. Remember the runtime complexity of DFS on a tree. In a tree that has n nodes and height of h, where h is between log of n and n, you can show that the runtime complexity is O of n. N is the number of nodes in this tree, and the memory complexity is O of h because of the call stack. So we know what the runtime complexity of DFS is. This allows you to find the runtime complexity of any recursive function, because all you're doing here is also DFS. So the runtime complexity and memory complexity that we calculated here applies to recursion as well. So in order to calculate the time complexity of recursion, you can draw its recursion tree, find out how many nodes are in this recursion tree, and then the runtime complexity would be O of the number of nodes in that recursion tree, and the memory complexity would be tightly coupled with the height of that tree. And I put a star here because in most cases we can say this. There are some exceptions, and those exceptions are when the breaking and combining steps are not O of 1. If the breaking and combining, the breaking into subproblems and combining solutions. If these two steps are all one, we are doing exactly what DFS is doing, and the runtime complexity would be O of n being the total number of nodes in the tree. However, if these two steps take more time than O of 1, you can't simply say the runtime complexity is equivalent to DFS because you're doing more work. We saw some examples of that, for example, the merge sort and quicksort. For most simple recursive functions, this holds, and this should give you a lot of insight. And the recursion tree should give you a lot of insight, not only for solving the problem, but also for finding its runtime complexity or memory complexity. So how many nodes are there in the recursion tree of the Fibonacci function? First, notice that the height of this tree is 5. We start from 5 here, and through this branch, which is the longest one, each time we subtract 1, and then we stop at f of 1. And as an estimate of the runtime, you can say at each level, the number of nodes roughly doubles. So I have 1 node here, then I have 2, then I have 4. Here, I don't have exactly 8, but again, we are calculating an upper bound, so you can say this is 8. And same here, you can say I have 16, although this is not accurate, but we are calculating an upper bound. So if you're calculating Fibonacci or f of n, you can say the upper bound on the total number of nodes in this recursion tree is O of 2 to the power of n. Exactly because we assume that at each level, the total number of nodes doubles. If you want to be more accurate, you can use math and show that this 2 is really 1.618, which is also known as the golden ratio that is attributed to Fibonacci. So as far as we are concerned, for calculating the total number of nodes in the recursion tree of the Fibonacci function, this tree has O of 2 to the power of n, or 1.618 to the power of n. And this would be the runtime complexity of our DFS on this tree. Now, I want to add another point here, which is about this important technique called memoization. Memoization is a very popular technique that is used to optimize the runtime complexity of recursive functions. If your recursion tree has duplicated nodes, for example, here, f of 3 is duplicated here, or f of 2 is duplicated here, then you can apply an optimization to your DFS. As you're running your DFS on this tree, you can say, hey, I have seen f of 3 before here, so I don't have to run DFS on this node anymore. I can just use memory. Same thing here, you can say I have seen f of 2 here, so as I'm doing my DFS, when I come back here and I'm about to go down this branch, I can remember that I already calculated f of 2 here, so I don't have to go down this branch. And in fact, if you look at the memoization algorithm, it is exactly DFS plus these optimizations that you just make sure that you go down the branches in your DFS that you have seen before. If you want to know more about dynamic programming, please make sure to watch my video on dynamic programming. The link is up here. So I would really hope that you take away this different perspective on recursion. Any recursion of your choice, or I should say any practical recursion, you can say the recursive function is really a recipe for creating the recursive tree. So this recursive function or recursive step is really a recipe to create this recursive tree. Once you have this, the function's execution corresponds to a DFS on this tree. The very first time that I saw this, it kind of blew my mind. I hope this is also an interesting concept to you. And I really hope this gives you some new perspective or tangible understanding of what recursion really is. In most cases, it really comes down to running a DFS on the recursion tree. All right, moving on. How do I know a problem has a recursive solution? I'm given a problem, maybe in a job interview, maybe at work, and I need to know how to solve it. How do I know it has a recursive solution? There are a few techniques that you can apply to see if there is recursion involved. The first thing is to see if there's a recursive data structure involved. What is a recursive data structure? For example, a tree is a recursive data structure because a tree consists of a root and several subtrees. Each subtree itself is a tree recursively. So if this is a recursive data structure, chances are that the problem that involves a tree, for example, they ask you to find something on this tree, chances are this involves recursion. This can be solved by recursion. Another example is a list. A list is also a recursive data structure. If you break a list into two sublists, each sublist is a list itself. So chances are that a problem that involves a list has a recursive solution. Other examples are graphs. BST, binary search tree. And in fact, in binary search tree, most problems that I have seen in binary search tree are recursive. So next time that you see any problem on binary search tree, recursion should be the first thing that comes to your mind because this data structure is highly recursive. Matrices are also another example of recursive data structures. So this is one clue for you to think about recursion. Is the problem that's given to me trying to do something on a recursive data structure or not? Another technique that you can apply is to see what's the simplest instance of the problem. So in here, we're really trying to start from the base case. For example, sorting an array is not an easy task. There are multiple algorithms for sorting an array. However, a very simple instance of this problem would be sorting an array of size 1. I'm pretty sure that each of you, including myself, can sort an array of size 1 while we are sleeping. This would be a very simple task to do. Once you found the solution to this, then maybe think about an array of size 2, then maybe think about an array of size 3, and so forth. So the goal here is to find the base case and then use that base case to go to the next instance of the problem that is just a little bit harder. So assuming I can sort an array of size 1, can I sort an array of size 2? If you think about it, that involves just merging these two subarrays. Another example of this technique would be finding the shortest path. Finding the shortest path in a graph can be a hard problem, and there are various algorithms that try to solve this. However, a very simple instance of this problem would be when I say find the shortest path, assuming that the shortest path length is 0. So how can I find the path from S to any other node in the graph, assuming that that path is 0? And it turns out that finding the path when the path length is 0 is actually very simple because in most cases, it actually doesn't exist. So the shortest path from S to itself is 0. The shortest distance from S to itself is 0 when my path length is 0. But the shortest path of S to any other node doesn't exist under this assumption that the length is 0. So there you have it. We just found the shortest path of S to any other node in the graph under this simplified assumption. I know it's not practical, but this is the simplified assumption. Now that you found this solution, change the length to 1. Can you find the shortest path when the length is 1? Then can you find the shortest path when the length is 2? So again, this gives you your base case, and then you find your way up from here and you will see that there is a recursion. And in fact, this is exactly what the Bellman-Ford algorithm is based on. The Bellman-Ford algorithm is a very famous dynamic programming algorithm. And as I have mentioned, every dynamic programming problem is based on a recursion, and that recursion's base case is exactly this. All right, now let's talk about our systematic approach for solving a recursion. Here, I'm trying to give you a bullet list of all the steps that you need to take to solve every recursion that's given to you. Once you figure out that the problem has a recursive solution, just follow this systematic approach and hopefully you can be able to solve that recursion. And it turns out that this systematic approach is very simple. All you need to do is to answer these questions. What is the base case? And what is the recursion step? Which, as part of this question, you're really also answering how do I combine the solutions to the subproblems. Now, once you answer these two questions, you already solved the problem. The problem is solved. All you need to do, remember that every recursion is really DFS. So all you need to do is to use the DFS template and convert the answers of these questions to a DFS-based function. And also make sure that you don't forget about the recursion tree. Drawing the recursion tree should be one of the first things that you do because it gives you a lot of insights for answering these questions. And in fact, this tree would be your best friend. Now, I know this might seem simple and you probably already know it, but I promise you, next time that you see any recursive problem, follow these steps one by one, and I promise you, you can solve that recursion. Let me show you some examples. Example number 1, given the root of a binary tree, find the maximum value in the tree. So I give you a binary tree, and all I want is to find the maximum value in that tree. Here's our binary tree. There are various numbers here. We want to return the maximum value. In this case, the maximum value is here. How do we solve this? You can pause the video here and think and see if you can solve this recursively. One solution that might come to your mind is to just run DFS on this tree and visit all the nodes and keep the maximum. That works, but in this case, we want to formulate this as a recursive problem using our systematic approach. So let's answer those questions and see if that works. if this has a recursive solution, which is very likely because we're working with a tree, which is a recursive data structure, let's answer the first question. What is the base case? What is the simplest form of this problem that I can solve? One answer to this would be, what if the tree is empty? For an empty tree, the maximum value in an empty tree, you can return none or minus infinity. I'll talk about why minus infinity can also be possible, but we just want to indicate that the maximum doesn't exist. And I promise everyone, even if they don't know computer science and programming, if you ask them that, hey, I give you an empty tree, find the maximum, they will tell you that it doesn't exist. So finding the base case is actually very simple. So we answered the first question. Let's answer the second question. What is the recursion step? How can I break this problem into subproblems? When a tree is involved, you can basically break the problem and correspond each subproblem to each subtree. What I'm saying is that you can find the maximum on the left side, find the maximum on the right subtree, and then combine the left maximum, the right maximum, and did you remember the root? So we have to combine these three values to get the max value in the tree. And the combining function in this case, yes, you guessed it right, is the maximum function. So all I need to do is to return the max of left max, which is the maximum value on the left side, with the root val, which is this one, and the right max, which is the maximum value on the right side. Notice that now I answered these two questions. All I need to do in the step 3 is to use DFS and write the recursive function. And one quick note about minus infinity here is that when you calculate this max, you're implicitly assuming that these values are not none. They actually did exist. If the left subtree is empty, you don't participate that empty value in the max. So instead of returning none and not participating that value that corresponds to none in max, you could return minus infinity, which is a don't care value for the max function. This is a very common technique that you see programmers use to write a more efficient code. All right, so let's move on to step number 3, which is nothing but DFS. Here is my DFS function. I use question number 1, my base case. If the tree is empty, I return minus infinity. At step number 2, I calculated, I had 2 recursive calls. So I call find max on the left subtree. I call it on the right subtree. I store them in 2 variables. And then I combine them using the max function and I return the result. Notice how our systematic approach worked by answering a couple of questions and then using DFS. All right, let's see a more complicated example, the coin change problem. This is a very famous dynamic programming problem and also a recursive problem. So given a list of coins and a total amount of money, find the minimum number of coins to make up that amount. You can use each coin infinite number of times. Here's an example. I have coins with values of 1, 2, and 5, and I want to build up the value of 11. How can I combine these coins to build up 11? There are various cases that you can combine these coins, but it turns out that the minimum number of coins that you can use is actually 3, which would be 2 coins with value of 5 and 1 coin with value of 1. Your function, your solution should return 3. And that's the output of our function. How do we implement this? Again, you can pause the video, think about this, use our systematic approach, and come back. All right, we have to answer to 2 questions. In this case, let's start from the recursion step. If I want to find the minimum number of coins to build up 11, let's show that with f of 11. F of 11 means the minimum number of coins that I need, assuming that these are my given coins. F of 11 represents the minimum number of coins that I would need to build up the value of 11. How can I break this into subproblems? So in order to break this into subproblems, you can think of what would be the step before this. I was either at 10 and I added a coin with value of 1 to get to 11, or I was at 9 and I added a coin with value of 2 and I got to 11, or I was at 6 and I added with a coin with value of 5 to get to 11. There is no other case. I have to be at one of these cases and add a coin either with value of 1, 2, or 5 to get to f of 11. And in order to do this optimally, I have to first build 10 optimally and add 1 coin to get to 11, or build 9 optimally and add a coin to get to 11, or build 6 optimally and add a coin with value of 5 to get to 11. So these are my subproblems. In order to solve this problem, I have to solve this problem and this problem and this problem. But the question is, how do we combine them? What is the combining operator in this case? And in this case, because we are minimizing, you can simply say, I should pick the one that has the minimum value. So my subproblems are these, and the combining operator would be a simple minimum value. And to be exact, it's minimum plus 1. So minimum number of coins to get to this one or this one and this one. But in each case, I have to add one more coin to get to 11. In this case, one more coin with value of 1. In this case, one more coin with value of 2. And in this case, one more coin with value of 5. Either way, I have to add one more coin. That's why we have this plus 1 here. So the combining operator is the minimum of each subproblem plus 1. All right, we answered the second question. What is the answer to the first question, which is what is the base case? In order to find the base case, remember for this tree diagram, we have to find the leaps, which means how far can I go down? 10 goes to 3 other values, 9 goes to 3 other values, 6 goes to 3 other values. How far can I go down? And it turns out that you don't want to go down after 0. If you get to 0, which means building the amount of 0, you can't really build a negative amount, assuming your coins are non-negative, which is the case. You don't want to go lower than 0. So how many coins do you need to build the value of 0? It turns out that you need 0 coins, so f of 0 can be 0. There is a case that you keep going down. For example, if you keep subtracting 2 from 11, you go to 9, then 7, then 5, and eventually you come to minus 1, not 0. So can you build a value of minus 1 or a negative value with coins that are all positive? The answer is no. So that's your other base case, which is if your input is negative, your output is invalid, meaning that there's no answer. So we return minus 1 in this case. You could return any other thing to indicate this was an invalid case. Nevertheless, this is a base case. So for negative input, I don't need recursion. For a 0 input, I don't need recursion. For any other non-negative or non-zero input, I will do recursion, which we discussed here. Now that we answered these two questions, what's the next step to completely solve the problem? You guessed it right. It starts with a capital D, DFS. So let's convert this to DFS. As you can see, this part corresponds to my first question, which is my base cases. And we have to be a little bit more accurate here for combining function. Each subproblem is really the amount minus that coin. For example, 11 minus 1 is 10, 11 minus 2 is 9, 11 minus 5 is 6. But we only participate the ones for which the output is non-negative. So if one of these subproblems returns negative, we don't participate that in our minimum function. So this is the same thing that we said before, we're just being more specific. Now, there is a chance that all of these values, all of these subproblems return a negative value. What does that indicate? That indicates that in any way that you go, you can't get to 0. That means this problem cannot be solved. So if that happens, if all of your subproblems return minus 1, in that case, you also return minus 1. Now that we are more precise and more specific here, we also convert this to code on the right side, which notice that this is still DFS, my base case, and also a recursive call for every branch of this tree. So I go through my coins, I call the recursive function just like I would call DFS on that subtree. And if the value is not negative 1, I participate that value in my running minimum. And at the end, I return minus 1 if all the paths turn out to be minus 1. Otherwise, I return the minimum value. So this, again, is nothing but DFS. Notice that we solve this problem, again, using that systematic approach by answering two questions and then using DFS to convert it to code. As you use your DFS, you actually use the answer to these two questions. You basically just convert them to code as they are, so there's nothing else to think about. So I hope these two examples give you some vision into how to solve recursive functions. So next time you see a recursive function, please follow these steps and let me know in comments if you were successful to use this technique and solve that recursion. All right, to summarize, we said every recursion is just DFS or corresponds to a DFS on the recursion tree. The root of the recursion tree is the problem that you're solving. The subtrees are the subproblems, which are recursive calls in practice, and your leaves are the base cases. Don't forget about the recursion tree. Problems on recursive data structure likely have recursive solutions. For example, trees, binary search trees, graphs, and lists. When you get a problem on these data structures, one technique to think about would be recursion. And finally, I presented to you a systematic approach to recursion, which consists of 3 steps. Find the base case, find the recursive step, and then the execution naturally follows DFS. And one more time, as you're solving recursive functions, make sure that you use the recursion tree. This is your best friend, gives you a lot of insight into solving the problem. Thank you so much, guys, for watching my video. Please make sure to like this video, subscribe to my channel, and also share this video with your friends. And hopefully I will see you next time.